Okay, u-Substitution with trigonometric integrals. There's two kinds of problems you're going to encounter. The first kind is when you have just a straight trig function rule like this. And you've probably seen those rules on your sheet. The integral of cosine of u du is equal to the sine of u plus c, which makes sense because the sine of u, its derivative, is cosine of u. Or similarly, you might see something like this. The integral of secant u tangent of u du is equal to the secant of u plus c. The other kind you might see are the kind related to the power rule, where you have u to the n du is equal to u to the n plus 1 over n plus 1 plus c. Okay, so we're going to deal with both kinds here today. So, I see number one, cosine of 5x. Well, that's kind of like this up here. So what I'm going to do is I'm going to let u equal 5x, so du will equal 5 dx. Problem, I don't have a 5 dx, so I'm going to put a 5 here and a 1/5 out here, which is okay because 1/5 times 5, or a fifth of 5, is 1, and multiplying by 1 does not change the value of an expression. So I'm going to rewrite this one as 1/5 the integral of cosine of 5x, 5 dx, which is good because there's my du, and the inside there is my u. So I can make the substitution and go, that's really cosine of u du, and the integral of cosine of u is sine of u plus c, and it's 1/5 because I had a 1/5 outside the integral. So, putting x back in, I get 1/5 sine of 5x plus c, and you could check that by taking the derivative using the chain rule. Okay, number two. This looks like one of the power variety because I say I have sine squared. So I'm going to let u equal sine of 3x because I'm going to let the u be what's raised to a power, and I see conveniently the derivative of that is cosine of 3x times 3 dx by the chain rule. Okay, well I don't have a 3, so I'm going to put a 3 there and a 1/3 out front. So I can rewrite that as 1/3 the integral of sine squared of 3x times cosine of 3x times 3 dx. Well, that's good because right there that's my du, and this here is my u. And it becomes especially clear if you were to write it like this, sine of 3x squared. Okay, so I have 1/3 u squared du after I make that substitution. So I get 1/3 u cubed over 3 plus c, and a 3 times 3 is 9, so 1/9 u cubed plus c. So I get 1/9 sine cubed of 3x plus c. In a calculator, you might see that written 1/9 sine of 3x cubed plus c, right? But usually we write the 3, the power as an index here on the sine, because it's on the sine function and not the 3x. Okay, let's look at two more. Okay, so here I have secant tangent. Okay, and I could take that 2 outside of my integral, because the 2 is just a constant. Alright, so now I'm going to let u equal 5x, so du is 5 dx. So I notice I don't really have a 5 dx, so I'm going to put a 5 here and a 1/5 out here. Well, 1/5 of 2, or 1/5 times 2 is 2/5. Secant of 5x, tangent of 5x times 5dx. Well, that's good because there is your du, there's your u, and there's a u. So when I rewrite this integral by substituting, I get 2/5 secant of u, tangent of u, du. Now by rule, I get 2/5 secant u plus c, and when I substitute the x back in, I get 2/5 secant of 5x plus c. And you can check that by taking the derivative. Okay, last one. Well, I noticed something. If I let u equal sine of x, that means du would be cosine of x dx. Well, let me rewrite this one in a slightly different order. It'll be easier for you guys to see probably. Well, now you notice there, right there is my du, if that sine of x is my u. So I get u du, so I get u squared over 2 plus c, or 1/2 sine of x squared plus c, which is usually written like this in a book, sine squared of x plus c. And you could check that by taking the derivative. Just remember to use the chain rule.